Hello, this is Math 111, and this is section 4.3. We're going to look at the very first rule, and let's play around with a few things first. Let's just say that the log base a of some variable x equals m, and the log base a of some variable y equals n. Then writing this in exponential form, this would be true, and this would be true. Just writing it as exponents. Well, now, if I multiplied x times y, that would be the same as multiplying these two together. But because these are exponents, that's the same as this. Okay, that's easy. So now I have this being true, x times y is equal a to the n plus n. What if I take the log of both sides? This would say the log a of x times y is equal to the log a to the n plus n. And those cancel out, they're inverse functions. So now I have log a of x times y equals m plus n. Oh, that's interesting. Look up here. Remember what n and n were equal to? There's m. Here's m. So I can rewrite that and say the log base a of x times y is equal to the log base a of x plus the log base a of y. So this is our first property. I touched upon that, I believe, in our last session towards the end, but this is a proof of that property. All right, so let's go ahead and answer these questions now. Okay, so let's take a look at these first few questions. All right, so this is the common log, which is base 10 of 25. Now, 25 is 5 squared. It's 5 times 5. It is 2.5 times 10. Let's take 2.5 because that's what they gave me here, times the log 10, that's 25, 2.5 times 10. Using our property, we know that that is the log 2.5 plus the common log of 10. Well, we know 10 to the first power equals 10, so this is 1. And they gave us this is 0.3979, so this is equal to 1.3979. Right? So log of 25 is equal to 1.3979. Well, the log of 75 is the same as log of 25 times 3, which is the log of 25 plus log of 3. We already figured out log of 25 is 1.3979. Just going to add to that 0.4771. And in the spirit of not doing it with this calculator, we're going to do this by hand. That's 10, carry the 1, 15, carry the 1, 17, carry the 1, 8, 1.8750. Awesome. All right. It says using evaluate the log 2.5 in example 1, calculate the log of 2500. Well, 2.5 times 1000 equals 2500. So this is the same as log 2.5 plus log 1000. Log 1000 is 3, and this is 2.5 is 0.973, so this is going to be 3.3979, whatever that number is. All right, awesome. All right, our second rule is that if you have a log base a of x to the k, and that's same as k log base a to the x. Should we take a quick second and prove this? Because they're actually very enjoyable to prove. All right, let's just let log base a of x. Let's see. Well, there's so many different ways we could think of this. This is just x times x times x times x times k times, right? Which would be log of a to the x plus log of a to the x plus log to a to the x. Dot, 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 all the way up, k times. And if we do repeated addition over and over again, that's just k times log base a to the x. So this is just a extension of the rule that we just learned. So if I have this, I know that this is log base 10 of x plus log base 10 y to the negative 3. Notice the negative 3 only goes to the y here. It's not outside the parentheses, so it just goes directly with the y, which means this is log base x plus negative 3 log y. And this is log x minus 3 log y. And this one, natural log of 3 plus natural log of x to the 1/2 plus natural log of the cube root of y. All right, now this is just a constant, natural log of 3, plus 1/2, bringing the exponent down in front, natural log of x, plus 1/3, bringing the exponent down in front of natural log of y. That's the answer for B. And here's our C. I'm running out of space, kind of got a little messy here. All right, we're gonna bring nothing. We cannot bring this down. What? We can't bring that down because that is not the natural log of x. That is the natural log of x cube rooted. And that cannot be simplified. That is different. Sure, we can simplify this, but we cannot simplify when the natural log is inside the parentheses. Okay? So this is not possible. All right, let's check out this, check it out. So I have 4x to the negative 1/3 root y, and this is all inside the common log. So we're going to break this up into each factor is going to be its own log first. And now each exponent is going to come down in front. Remember that a square root is a 1/2. If these were all the same exponent, then we could collect like terms, but they are not, or the same variable. There we go. All right, and our next property. So we talked about happens when you divide two things, what happens when, or multiply two things, what happens when you divide these two things. So when you multiply two things together, you add them with exponents. But if I have two exponents being divided by each other, you subtract them. So this means that if you have two things being divided inside the log, they do not become its sum, but they become their difference. We can use the rules that we already have to prove this. Log base a of x over y is the same thing as just x times y to the negative 1, which is log base a of x plus log base a of y to the negative 1. We'll bring that exponent down. It becomes negative 1 in front, so minus, and voila. So we can use the same rules we have to prove this already. So let's take a look at how we can write this as sum or differences. We have log x to the third plus log y squared minus log 100, which would be 3 log x plus 2 log y minus, this is a common log of 100, 2. Log base a of the square root of x squared plus 2 minus log base a of x plus 1 cubed. This is 1/2 log base a of x squared plus 2. There is nothing I can do with the sum inside. I can't make it into a multiplication or anything else. A sum has to stay a sum inside the function of a log. Right? I can bring the 3 down here though, and that is our most simple form. Right. Let's break this one up as a product of sum or differences. This would be square root of x minus 1 plus log of x squared, oh, that's a minus, because it's in the denominator, x squared plus 4. We can bring the 1/2 in front. Can't do anything with the inside there. Can't bring the 2 down because it's a sum. So there's nothing I can do with it. I cannot bring the 2 down. It has to be in front of everything as a sum. That just doesn't work. Okay. All right, now we're going to use these rules backwards, and we're going to combine these into single things. So here we're adding. So for a, we're adding, so it's going to be a multiply. So this is log base a. Just trying to erase that. There we go. So we have log base, struggle. Log base a multiply 18. Boom, because that's 3 times 6. That's log base a 3 times 6. Let's see that step out. All right, b. Take them one step at a time. We have the natural log of 64 raised to the 1/3 plus the natural log of x to the 1/2. All right, this is going to be the natural log of the cube root of 64, which is 4. Plus, this is the natural log of the square root of x. All right, these are adding, so now we can take this product, the natural log of 4 root x. Single log. Okay. And this is going to be 3 log base 10 of 5 minus 1. Now, how could I write 1? So I'm going to have the common log, which is log base 10, of something equals 1. So what do I have to raise 10 to? What would 10 to the first power equal? That needs to be 10. So we're going to have 3 log 5 minus log 10, which would be the same as log 5 to the third minus 1. Sorry, minus log 10. We didn't want it as 1. What a struggle bus. All right, and this is log 125 minus log 10, which is log 125 divided by 10, which is the log of 12.5. All right, and now we need some space for d. Let's do it over here. All right, move this all over, d. So we have the log base a of x plus the log base a of the square root, bringing this 1/2 up here, of x squared plus 1 minus the log base A of 3. So we're going to multiply this and then divide the 3. So we have log base A of x times the square root of x squared plus 1 all over 3. And here we go, one more down here. Let's zoom that in so everyone can see it. That is log base A. So this is our original problem we're starting with. And we're going to pop that guy up. And now we're going to take the log base A of x cubed over x squared plus 1. There we go. Single logarithm. All right. Measuring the pH of a system. Solution. The pH of a solution is a measure. Okay, so the pH of a solution is a measure of the concentration of hydrogen ions in the solution. This concentration, which is denoted H+, is given the units of moles per liter, where 1 mole is 6.02 times 10 to the 23rd molecules. Because concentration of hydrogen ions can have several powers of 10 from one solution to another, the pH scale is introduced to express the concentration in a more accessible terms. The pH of a solution is defined as pH equals the negative log of H+. Right? Find the pH solution A, where the hydrogen ion concentration is 10 to the negative 4 moles per liter. All right? So let's get all of this information. Why 1 mole is this many molecules, but H+ is given in moles per liter. Right? So H plus 10 to the negative 4. So this pH would just be negative log. This is H plus because it's in moles per liter. And this is 10 to the negative 4. So that would just have a pH of 4 because this would be, bring the negative down, negative 4. 10 to the log base 10 of 10 is 1. Negative 4, which is 4 times 1, which is just 4. Right? Find the pH solution B, whose hydrogen ion concentration is this, moles per liter. All right, we're already here. So the pH is equal to negative logs 4.1 times 10 to the negative 8, which would be negative log. Let's do it this way. We can do it this way. So many ways to do this. Let's do negative 4.1 plus, this whole thing is got the negative around the whole thing. Log 10 to the negative 8. That's using our recent adding, multiplication to adding. This is, sorry, we need this negative 8 there. Yoop. And let's find out what log 4.1 is on our calculator. So log of 4.1 is 0.61. This is negative 0.612789 minus 8, which is negative 7.387, which is 7.387. If a pH solution has a pH of 9.2, what is the concentration of hydrogen ions? All right. Ouch. Right, so we're going to solve 9.2 equals negative log h plus, right? There's so many ways I could do this. I'm going to make this into log 0.2 equals log of h plus to the -1. And this is log base 10, so this says 10 to the 9.2 is equal to 1 over h plus, right? Which means h plus is equal 1 over 10 to the 9.2. 10 raised to the 9.2 power is this. And if I take the reciprocal of that, 1 over, I get h plus equals 6.31 times 10 to the -10. There we go. Find the pH solution whose hydrogen ion is 3.2. So again, we're just going to use our -3.2 times 10 to the -8. Use our formula that says this is log of 3.2, and we're adding, I'll just write it out quick. This goes to -8. Log of 3.2 minus 8, -7.495, negative, positive. There we go. All right, and that wraps up section 4.4 on properties of our logarithms.